Welcome to organic chemistry. As you probably already read, organic chemistry, in like its most simple sense, is the study of carbon-containing compounds. Now, there are some substances that contain carbon that we don't classify as organic, but in general, if it contains carbon, it's most likely an organic compound. And I think it's kind of funny when you think about it, to think that the entire field of chemistry, the study of matter, can be broken into two main parts, organic and inorganic. That's like kind of the first branch of studying chemistry, is we have inorganic and organic. So if you think about it, we have broken the whole field into two parts, one which covers predominantly one element of the periodic table, and then the rest, the other 117, are in the other. I mean, that's an oversimplification, but it does seem kind of funny when you think about it. Except there are about 500,000 known inorganic compounds, and that's a lot. But there are over 9 million known organic compounds, with more being added, discovered, or synthesized every day. So in that perspective, when looking at it from that angle, I can kind of understand that classification and why carbon-containing compounds end up getting their own field entirely. So why carbon? What's so special about carbon? Why is it that when scientists think about life on other planets, why do they always assume it would still most likely be carbon-based? What's so special about carbon? Well, I'll give you a little bit of a hint. It comes down to diversity. In order to support life and the molecules of living things, which is actually how we started defining organic chemistry originally, we need a molecule, or we need an element that is able to make lots of different kinds of things. Because if you think about all of the parts of you, even at a macro level, let alone at a micro level, they're very, very different. And so carbon allows for that. But why? So let's start with carbon is able to form stable bonds with other carbon atoms. So essentially like with itself. Like carbon is able to form carbon bonds. Specifically the word, you don't need to know this, but it's cool, is catenate. It can form like all the chains of carbon, catenate into these chains, or they can be rings, or they can be branches. And carbon isn't the only atom to do that. Silicon also actually can catenate very well, form bonds with itself in a diverse arrangement as well. But silicon has a pretty high affinity for oxygen. And so sometimes when silicon, ignore that, when silicon would otherwise catenate, it will react with oxygen instead. And in an environment like Earth, which has a relatively oxygen-rich atmosphere, that's not going to support life if the silicon is constantly instead reacting with oxygen rather than itself. So carbon can catenate, it can link up over and over and over again with itself, and the bonds are particularly strong, don't fall apart really easy. Another thing about carbon is it doesn't just bond well with itself, it bonds really well in a covalent bond, that's a particularly strong bond, with many other elements. And that goes back to carbon's electronegativity. And you don't need to know this, but I think it's interesting. Carbon's electronegativity, which you might remember from 121, is the force of pull on shared electrons in a bond, is 2.5. But that's neither high nor low, which is actually why carbon does that very thing, form stable bonds with many other elements like oxygen and nitrogen and phosphorus and sulfur. Carbon's electronegativity is too low to steal other people's electrons, but also too high to have it stolen from it. So carbon doesn't really make ionic bonds very well. Instead, because of this neither too low nor too high, it's kind of a Goldilocks situation, just right, it shares very, very well. And then finally, it can form many bonds and many bond types, more than a lot of other elements. So this goes back to some information you've learned in previously chemistry courses. So let's think about the Lewis structure of carbon. Carbon has 4 valence electrons, so that's 4 electrons in its outermost energy level. So what you're seeing there is the Lewis structure of carbon. So because of that, carbon likely forms 4 bonds in order to fill its valence shell, because carbon would be the most stable if it had 8 valence electrons in order to be isoelectronic with that nearest noble gas, neon. I pointed up there like you guys can see my periodic table. So based on that, based on the fact that carbon has 4, it actually can do that. It can fill its octet in multiple different ways, as shown here. Carbon could form 4 single bonds, so share 4 times. Carbon could form 2 single and 1 double, or 2 double, or 1 triple and 1 single. This is a lot of diversity in just even the way carbon can bond, and that's going to create diversity in the structure and the shape of the molecule. And again, silicon is in the same group as carbon, and so also has 4 valence electrons. But silicon, based on its size, isn't quite able to form very stable double and triple bonds, and so we have a reduction in its ability to create diverse. This is all about diversity. So based on all of that, carbon is like the queen when you're playing chess. And the queen is one of the most important pieces when you play chess, because she can move in all the different ways. She's like this combination of everybody else's movements, and it makes her very deadly on the chessboard. Well, carbon can bond in a bunch of different ways with a bunch of different things, and with itself over and over and over in a bunch of different ways. And that creates that 9 million organic compounds versus the 500,000 inorganic. So for example, there we go. Whoa. Let's try one more time. For example, I just chose some molecules to kind of highlight this. We have oxytocin, the molecule of love. So this is like the bonding hormone, particularly like between a mother and a child or between lovers. And you can see, we'll learn more about that kind of structure, but it's predominantly carbon. There's rings, there's double bonds. Here we have not the molecule of love, but the molecule of being awake, caffeine. And then down here, the C10H22, we have, this would be called decane, and it happens to be a component in gasoline. But the reason I chose decane, it might seem kind of boring, is linear decane, which we'll talk more about linear later. We have the 10 carbon atoms and 22 hydrogen atoms. Actually, there are 75 different compounds out there with that exact same formula, with 10 carbon and 22 hydrogen. And how can that be? It goes back to what we were just talking about. Carbon can bond in so many different ways that we can have completely different substances that are still made of the exact same elements in the exact same ratios. And that's what you've been learning about with structural isomers. Structural isomers are going to have the exact same chemical formula. So here, like this butane, 4 carbons, 10 hydrogens. So the same elements in the same ratios. But if they're connected in a different way, they might end up being different compounds altogether. So you'll notice in organic chemistry, especially as opposed to inorganic, we move away a lot from using molecular formulas because it doesn't convey very good information. How are those bonded together? If I say C4H10 to another chemist, they're going to be like, which version of that? And as you can see in this table, it gets drastic pretty quickly. And these truly are different substances. I know on paper they don't really look that different, but structurally they end up having different boiling points, sometimes even different chemical reactivity. In this case, our linear butane is probably going to have a slightly higher boiling point because those London dispersion forces are going to be able to be a little bit more strong and impactful in a flat linear molecule that can stack on top of each other, as opposed to a more bulky branched molecule, even though they actually have the exact same molecular weight. So this practice problem, I'd encourage you to pause the video and kind of think about it for a second. Which of these represent structural isomers and which are simply the same compound? Now, I'll be really honest, I'm being really mean here. This is totally a trick question. They are all the same compound. Not one of them represents an actual structural isomer. And the reason I like to throw this question out there is because it really shows that you have to think very three-dimensionally about organic compounds, because what they look like on paper doesn't necessarily reflect very well what they are in real life. And so I want to highlight this one, where's my mouse, in particular. You might be able to see really well, like this is a linear, this is also linear, so these are identical, but this one I think is the harder one to see, and this is a benefit of having a model kit where you can actually play with it in the 3-dimension instead of just trying to look at it on paper. So I left off the hydrogens for simplicity. So here is essentially that first one there, shown right here. Let me do it that way. So I have a 5-carbon chain with a 1-carbon group off of the 3rd carbon, right? Now, if I can turn this structure into that structure without snapping my model kit apart and only by rotating, because molecules really do have rotation in space, especially around single bonds. And so if you notice, so this is a 4-carbon, so 4 carbons with a 2-carbon chain off of it. So do you see how I did that? I didn't have to snap anything off. So therefore, these are actually not structural isomers. They're the exact same substance, but they've just been drawn in a slightly different way. And since molecules really can move and spin and twist in space, you have to get kind of good at thinking about that, thinking about them 3-dimensionally, which I'll be really honest, is kind of hard for me. So I am very much a check with the model kit kind of person. So one thing I want to just talk about real quick before we go is this class has another chemistry class as its prereq. So what is important? You learned so much in Chemistry 121. What's the most important stuff that's going to follow you into this class so that you can review it as needed? Some of you took 121 last quarter. Some of you, it may have been 6 years ago. So I just want to identify the most important content from 121 that you'll hear me talk about a lot. As you learned in 121, you'll remember from 121. And I don't say that to make you feel bad if you don't, but just so that you can identify, oh, put a little star in your notes. This is going to be a place I need to go back. So these are the 5 topics and their location in our current textbook on where you can find them that are most important for 131. And that's chemical bonding and polarity, which you'll find in chapter 3 in those sections. Lewis structures, you already saw me reference those in this lecture, also in chapter 3. So chapter 3 was very important. Intermolecular forces, this is going to come up a lot. So if you aren't really familiar with London dispersion, dipole-dipole, or hydrogen bonding anymore, go back and review them, especially as they relate to properties like boiling point and solubility. Equilibrium comes up now and then. I think the first 3 are probably the most important. And then as we move into the quarter, we will talk acids and bases. And so you might want to review the pH scale, not calculating pH, but just the pH scale. What's an acid? What's a base? How do I tell from a chemical formula? So good luck. We're going to have a great quarter.